Welcome, grade 9 students from St. Paul American School, Clark. We are jumping straight into a massive foundational topic today. We're looking at Geometry Unit 5, Lesson 8, Radian Measure and Arc Length on the unit circle. Get ready because this is the exact moment where math shifts from just human-made inventions to the literal, natural language of geometry. Okay, let's dive right into our agenda. We'll hit our lesson objective, explaining the unit circle, defining radian measure, finding arc length, a common misconception check, and finally, a quick check and recap.
Section 1. Lesson Objective.
So for this explainer, the goal is basically to upgrade your whole mathematical toolkit. First up, we're transitioning from measuring angles in degrees to a way more natural method called radians. Second, we're going to make sure you deeply understand the unit circle. And third, you'll learn how to calculate arc length using those radians. You know, degrees are great and all, but just wait until you see how radians make literally everything click into place. Section 2. Explaining the unit circle. Our source material gives us a beautifully crisp definition. The unit circle is simply a circle of radius 1 that's centered right at the origin of a coordinate plane. I really want to emphasize that phrase, radius of 1. That number 1, it's the absolute magic number that makes everything else we're about to cover work so seamlessly. When you picture the origin at 0, 0, notice how the angle, which we call theta, starts from the positive x-axis and rotates counterclockwise. The point at the end of that angle sits exactly on the circumference. And because this is a unit circle, the direct distance from the origin to that point is exactly 1 unit. It really is that simple.
Section 3. Defining radian measure.
Now, think about the arc that angle creates. Any angle corresponds directly with a very specific portion of the circle's circumference. We call that the arc spanned by theta. When you open up that angle, it traces a specific path right along the very edge of the circle.
So what exactly is a radian? Well, it's defined as the angle that intercepts an arc with a length equal to the radius of the circle. Let's break that down because it's a real game changer. Unlike degrees, which are honestly just an arbitrary measurement humans made up, like some ancient civilization just decided a circle has 360 parts, a radian is directly tethered to the physical geometry of the circle itself. It's the angle you get when you take the radius and wrap it perfectly along the circle's outer edge. This shows the massive night and day difference between a degree and a radian. A 1-degree angle is just a tiny, microscopic sliver of the circle, specifically 0.01745 radians. But a 1 radian slice, that is a hefty, substantial piece of the pie. In fact, 1 radian is roughly 57.3 degrees, so it's a way larger unit of measurement. Which brings us to an absolutely crucial point. On the unit circle, the radian measure of an angle is the exact length of the intercepted arc. Because our radius is exactly the real number 1, without units like feet or meters muddying the waters, the radian measure and the arc length become the exact same real number. If your angle is 1 radian, your arc length is exactly 1. Boom! Section 4. Finding arc length.
Let's check out the arc length formula. S equals alpha times r. Mapping this out, S stands for the arc length, alpha is the central angle, and r is the radius. So in plain English, your arc length equals the central angle multiplied by the radius. Let's connect that formula right back to the unit circle. If r is exactly 1, then, according to our formula, S equals alpha times 1, which means S simply equals alpha. This perfectly proves our earlier point. The length of the intersected arc is exactly the same number as the radian measure of the angle inside. Worked example, finding the arc of 90 degrees. Now, I want to pose a question directly to you, grade 9. What is the exact arc length of a 90-degree angle on the unit circle? I want you to really engage those problem-solving skills for a second. Picture the unit circle, think about what a 90-degree angle looks like, and remember our new rule about radians. Let's see how this all comes together step by step. Step 1, to use our arc length concepts logically, we've got to convert those degrees over into radians. We do this by multiplying the degrees by pi radians over 180 degrees. For step 2, we calculate 90 times pi over 180. That simplifies exactly to pi over 2 radians. And here's the grand finale of our example. Because we are on the unit circle and the radius is precisely 1, the arc length S is also exactly pi over 2. I mean, just think about how beautifully simple that final step is. The converted radian angle actually is the arc length. No complex secondary math required. Section 5. Common misconception checks.
Now, listen closely to this exact quote from the source text. This formula only works if alpha is in radians. If you take 90 degrees and plug the number 90 directly into the S equals alpha times R formula, you're going to get an arc length of 90 on a circle that only has a radius of 1. That is a completely wrong answer. Always, always convert your angle to radians first before calculating.
Section 6. Quick check and recap.
Okay, time for a quick mental check. If an angle is exactly 1 radian on the unit circle, what is the length of its intercepted arc? Take a brief second to picture it. Got it? If you said 1, you are absolutely correct. The length equals the radius, and on a unit circle, that radius is just 1. Excellent job.
To wrap things up, here are the 3 core takeaways you need to remember. First, the unit circle has a radius of exactly 1. Second, radians powerfully link angle measurements directly to physical arc lengths. And third, our arc length formula, S equals alpha times R, absolutely must use radians.
Finally, I want to leave you all with a bit of a mind-expanding thought. If humans arbitrarily invented 360 degrees just because it's a nice, easily divisible number, are radians actually the true natural language of the universe? When you see how elegantly radians tie geometry together, it for sure feels that way. Thank you so much for joining me in this explainer, Grade 9. Keep asking questions, keep focusing, and I'll catch you next time.